Hello dear students, welcome you all. In this lecture, I am going to take up some questions related to the topic that I have discussed in the earlier lecture, right? In the earlier lecture, I have discussed about the general properties of atomic nucleus, right? I have covered all the properties of the atomic nucleus, right? Now, in this lecture, I will take up some questions that are asked in different competitive exams. I will cover up only those questions which are related to those topics, right? So, first of all, I am starting with the questions that are asked in the IIT JAM exam, right? So, you can see here the question is the first question: if Me, Mp, and Mh are the rest masses of electron, proton, and hydrogen atom in the ground state, right? With energy given minus 13.6 electron volt respectively, which of the following is exactly true, right? Now, here in this question, the concept of winding energy has been used. First of all, we have to understand the question. We know very well what is winding energy of the atomic nucleus. Winding energy is equal to the difference between the mass of proton plus mass of neutron minus mass of the nucleus so formed, right? Za. This is the binding energy, right? Now the same thing is applied here. Here, instead of nucleus, we have an atom, and the atom is hydrogen atom, and it is formed by the combination of nucleus plus electron, and the nucleus contain only one proton, so it is the case of 1H1, right? So here we will have mass of proton plus mass of electron minus mass of the hydrogen atom. This is the binding energy, right? Because in case of atom also, when the nucleus and electron join together to form a stable system, that is atom, some of the energy is needed. That energy is called winding energy. So mass of proton plus mass of electron minus mass of hydrogen atom. So from here I got mass of hydrogen atom is equal to mass of mass of proton plus mass of electron minus binding energy, right, divided by c square. That will give me the mass, right? Now I can put the values if I want to put here, but I have given the value of the winding energy, and it is minus 13.6. So the equation becomes mass of proton plus mass of electron plus 13.6 divided by c square, and it is electron volt, right? So this is the answer. This is the correct option, and it is given here, right? So this is the correct answer, right? So, this is the way of solving this question. The concept that is used here, it is the binding energy concept, right? Now I am going to the next question. The question is, you can see here, a neutron of mass Mn is equal to 10 raised to power minus 27 kilogram, approximately the mass is given, is moving inside the nucleus to be a cubical box, right, of size 10 raised to power minus 14 meter with impenetrable walls, right? Take H cut is equal to approximately this value given, 1 mega electron volt, this one, right? An estimate of the energy in mega electron volt of the neutron is now. Here, although this question is not directly linked with that discussion that I have made in the earlier lecture, here the concept of particle in a box. Particle in a box. It is a topic of quantum mechanics. We know very well then when particle is confined in a one-dimensional box, energy is equal to h cut square upon 2m n pi upon a or L, we can take whole square. Here is the dimension of the box. If the box is three-dimensional, what equal sides, then this expression becomes En is equal to, now En will become Nx, Ny, Nz. That is equal to h cut square divided by 2m into pi square upon a square all the sides are equal, right? If the sides are not equal, it becomes a square plus b square plus c square, right? So then I have nx square plus ny square and nz square. These are the three quantum numbers associated with the three directions, right? Now here, it is not given when whereas this particle is in the ground state or excited state. So we have to consider the ground state. Means this all they are 1 1 1. So 1 plus 1 plus 1, it becomes 3. So the expression becomes 3 by 2 into h cut square, right? It is given here already, right? 3 by 2 h cut square upon m, right? A square into pi square. You can see here 3 by 2 h cut square pi square mn mass of neutron A square. So the rest of the things are to put all the values that are given here, and the examiner has given only approximate value in order to make the calculations simplified. So after simplification, you will arrive at this value 15 mega electron volt. So the examiner has asked you that you please estimate the energy nearest value. So although 15 mega electron volt is not given anywhere, but if we take the closest value, then this can be the answer, right? So this is the next question. Now I am going to the next question. Again, this question is taken from the binding energy per nucleon curve, right? I have told you in that lecture that this is the most important topic, right, in nuclear physics, that is winding energy and average winding energy and winding energy per nucleon curve. So here the question is, the following histogram, this histogram is shown here, represents the winding energy per nucleon, right, in mega electron volt as a function of mass number A of the nucleus, right? A nucleus, now the condition, the situation is given, a nucleus with mass number 180 fission into two nuclei of equal masses, right? We know very well, if we recall that graph, that all those nuclei which are on this side of the graph, they have the tendency to go here toward the higher side of binding energy per nucleon in order to achieve the stability, and they undergo fission, right? Whereas all the nuclei which are here, they want to go here, they will undergo fusion, right? So these are two processes. Now here examiner has given that a nucleus with mass number 180, approximately 180 is here, corresponding winding energy per nucleon is this one, it is 4 mega electron volt binding energy per nucleon, right? Fissions into two nuclei of equal masses, it means A gives you A by 2 plus A by 2. So 180 gives you 90 plus 90, two nuclei, right? Now 90 will be here, right? You can see here the winding energy is 6 mega electron volt. Now we have to calculate the winding energy of the parent nucleus and the winding energy of the daughter nucleus. So nuclei. So as far as parent nucleus, mass number 180, so winding energy is equal to 180 into, what is the value of winding energy per nucleon? It is 4. So it gives me 720 mega electron volt. Now if I come to the daughter nuclei or product nuclei, 90 plus 90, so 90 multiplied by 6, right, plus 90 multiplied by 6. So it gives me 540 plus 540 mega electron volt. So it will give me 1080 mega electron volt, right? So now what is the amount of energy that is released, right? Obviously I told you that when the fission takes place, the heavy nucleus split into two nuclei and the energy is released. That will be the difference between the winding energy between this one and this one, right? So if I take the difference of this term and this term, right, that is 1080 minus 720 6, right, 360 mega electron volt of energy will be released. This is the correct answer, right? So this was a question. This was the question from binding energy per nucleon curve, right? I'm going to the next question. Here, the question is a very simple question that is asked from the first topic of that chapter, that is linked with the nuclear radius. R is equal to R naught A power 1 by 3. This was the relation. Two spherically nuclei having mass number, this one with radii, this one, the ratio. So we know R1 is equal to R naught A1 1 by, R2 is equal to R naught A2 power 1 by 3. So R1 upon R2 is equal to A1 upon A2 power 1 by 3, power 1 by 3. So A1 is you have given 216, 64 power 1 by 3. It is solved here. You can see 1.5. 1.5 is the correct answer. So very simple question. I have seen another question of this type in another exams, right? So we have to remember it, how we can calculate the radii of different nuclei by comparing their mass numbers, right? Now I am going to the next question. In the coming lectures, I will cover all these questions. First of all, I will discuss the topics, and then I will take all these questions, right, one by one. Now, this is the question that is again from winding energy per nucleon graph, right? So the question is the variation of binding energy per nucleon, right, with respect to the mass number of the nuclei is shown in figure. We know very well this side is binding energy per nucleon and this is the mass number A. We have discussed this graph in details in the lecture that is exclusively about the winding energy per nucleon, right? Now the question is, consider the following reaction, right? 92 uranium 238 convert into lead 82206 plus 10 protons plus 22 neutrons, and the second reaction is also given. Here we have 6 electrons. Which of the following statement is true for the decay modes of these two decay modes? Both A and B are allowed, both 1 and 2 are forbidden, one is forbidden, second is allowed, same thing, right? Now first of all, compare whether the charge is conserved or not, right? Mass number is conserved or not. So as far as charge number, I mean number of protons, 92 on this side, we should have 92 protons on this side, right? So it is 82 plus 10 makes 92. So done, Z is conserved proton number. I am talking about the proton number, right? 238 mass number, 206 plus 10, 216 plus 22, 238. So A is also conserved, right? It means the reaction is allowed from these two perspectives. Now come here, 92 plus here we have 82 plus 8 into 2, 8 alpha particles, so 8 into 2, 16, right? So Z is 82 plus 16, 98, right? And here we have 92, so it is not conserved. Don't consider electrons because electrons don't belong to the nucleus, so the number of proton is not conserved. What about the mass number? 238, right? 206 plus 8 into 4, 32. So mass number is conserved, right? A is 238 on both the sides, while Z is not 98 on both the sides. So this reaction is not allowed. So the correct answer is, although they have written here C, but the correct answer is D. 1 is allowed and 2 is forbidden, right? This is the correct answer, right? So now I am going to the next question. The question is, right, a nucleus has size of the order of 10 raised to power minus 15 meter. Consider an electron wound with the nucleus. The estimated energy of this electron is of the order of, right? We know very well that the size of the nucleus is of this order. and electron is bonded with the nucleus, we have to estimate the energy. So in order to estimate the energy, first of all we have to estimate the momentum. So P is equal to H upon a lambda. Now H is Planck's constant, lambda is what? It is the wavelength, right, associated with the nucleus. So the wavelength associated with the nucleus will be of the order of its size, right, that is 10 raised to power minus 15 meter. So I put this value, so I got momentum. When we are looking at the wavelength of the nucleus, the wavelength should be at least equal to this size, or it should be less than. Otherwise, it is not possible that the nucleus has wavelength. If the wavelength is greater than the size, then how it is possible that that wave can represent the nucleus? So the wavelength should be either equal or less than the size of nucleus. So here they have taken equal. So this is the momentum. So then calculated the energy, E is equal to P square upon 2me, this one, and then it converted into mega electron. So this is the correct answer, right? 1.5 into 10 raised to power 6 mega electron volt. So the correct answer is of the order of this, right? Next question is, for an atomic nucleus with atomic number Z and mass number A, which of the following is correct? Let's look at the different options. Nuclear matter and nuclear charge are distributed identically in the nuclear volume. This is wrong, right? Nuclear matter and nuclear charge are distributed identically in the nuclear volume. This is not correct, right? We know that the nucleus possesses quadrupole moment. We have seen in that case, and in some cases the distribution is not symmetrical, right? In some cases it is symmetrical, but we can't say that it is distributed identically, right? So this option is not correct. Dropped. Nuclei with Z greater than this and A greater than this, omit. It is correct, right? We know very well. Although I will cover this topic in nuclear radioactivity, but we have to accept here that this is true, right? The surface contribution of winding energy is proportional to this. It is also true. Although this is related to the the formula of the winding energy of the atomic nucleus that we call CF von Weizsäcker formula, binding energy per nucleon formula, that I will drive and discuss in the coming lectures, but it is also correct. We have to consider here that directly that it is correct. The last is beta decay occur when the proton to neutron ratio is large, but not when it is small. It is again wrong, right? This will become more clearer to you when we will discuss the chapter radioactivity, right? Because beta decay, whether it is beta positive decay or beta negative decay or electron capture, they can take place, right? If the number of neutron is high, right? If the number of proton is high, right? So any of these number, if it is high, then these three process, electron capture, they can take place. I will discuss this in details. So n upon p or p upon n, I can't say that it is large or it is small. It can has both situations. So they are talking about the beta decay in general. So it can take place when this ratio is large and when this ratio is small also. So again it is wrong. So correct answer is this, right? Now the next question is, if I have left with any question, yes. The mean momentum P of the nucleon in the nucleus of mass number A and atomic number Z depend upon. Now again they are talking about the momentum. So momentum, when we are talking about the momentum, we have to take into consideration one relation, that R is equal to R naught A power 1 by 3, and R is of the order of, R is what? Radius of the nucleus. It is of the order of wavelength. So lambda is equal to, or I can say R naught, or I can say lambda directly proportional to a power 1 by 3. Lambda is what? Wavelength associated with the nucleus. So the momentum P is equal to h upon lambda. So obviously P inversely proportional to a power minus 1 by directly proportional to a power minus 1 by 3, or I can say P inversely proportional to 1 upon a power 1 by 3, right? Because lambda directly proportional to this, right? So P directly proportional to a power minus 1 by 3. It is the correct answer, right? Momentum, right? Mean momentum of a nucleon when it is inside the nucleus, right? So this is the correct answer. This is the way of solving this question. You can see here, right? Sometimes I have seen a question which the average energy of the a nucleon is also asked, and there this relation is also used. Average energy, right? It is also directly, if the momentum is directly proportional to this, then the average energy is also proportional to a power minus 1 by 3. The same logic is applied here. So this is about this question, right? Look at the another question if it is left. I think yes, one question is left there. The relation between the nuclear radius r and the mass number a that is given by this implies that now look at the different options. The central density of the nucleus is independent of a. It is clear, right? The density of the nucleus is independent of a. It is true. The volume energy per nucleon is a constant. This is wrong, right? The volume energy per nucleon is a constant, right? So it is, I think, wrong, because volume energy per nucleon, right? We will calculate it in the coming lecture, as I told you that when we will discuss it in the second chapter, or in the chapter of nuclear models. So the volume energy per nucleon is not a constant, but it depends upon the mass number. So I think it is wrong. The attractive part of the nuclear force has a long range, right? The attractive part of the nuclear force has a long range, right? So again, I think it is wrong, because nuclear forces, although the attractive part has large range as compared to repulsive part, but we can't say that it has a long range, right? So it is again wrong, right? The nuclear force is charge dependent, right? The nuclear force is charge dependent, right? Charge dependent, oh, it is again wrong. I think the options are I don't know how they have written a comma b comma d, but I think the correct answer is this one, right? In this question, because nuclear forces are charge independent, right? So I think this was the last question of these questions, right? Now I'm going to take up the questions of GATE, right? GATE exam. So the first question is the basic process underlying the neutron beta decay, right? Neutron beta decay means neutron convert into proton plus electron plus anti-neutrino. Although, as I told you, I will cover it in details in the radioactivity chapter, but here I can simplify this question with the help of a quark model also. So here they are basically down quark and up quark, right? Down quark, they are representing this decay in terms of quarks. We know very well that what is the quark content of neutron and a proton. So for neutron it is down down up, and for proton it is up up down plus electron plus anti-neutrino. So you can see it is the conversion of down quark into up quark plus electron plus this. The correct answer is this. You can see here, right? This is the answer to this question. This question is solved with the help of a quark model, right? Although this question is from beta decay, that is in radioactivity chapter. Let me change the color. Okay. Now let's go to the next question. The ground state wave function of deuteron is a superposition of S and D states, right? Which of the following is not true as a consequence? I have discussed the properties of deuteron, and we have seen that the ground state is a mixture of S and D states, right? Now the different properties of deuteron are given here. Which of the following is not a true as a consequence? It has non-zero quadrupole moment, it is true. The neutron proton potential is non-central, again true. The orbital wave function is not spherically symmetric, it is also true, right? The Hamiltonian does not conserve the total angular momentum, it is wrong, right? Hamiltonian conserve the total angular momentum. This is the property in case of deuteron. So this is the wrong option. All these options are correct. Now if you don't know about the Hamiltonian, right, then obviously you can approximate the correct answer, because these three properties you know very well, that non-zero quadrupole moment, neutron proton potential is non-central, orbital wave function is not spherically symmetric, right? But this, if you don't know about this, you can take a guess on this. So Hamiltonian in actual, right, I have not although covered it there, but the Hamiltonian for the deuteron does not conserve the total angular momentum. So this is the correct answer, right? Again, deuteron has only one bound state, right? With spin parity, spin 1 and parity positive, isospin 0, all these are discussed. Electric quadrupole moment, this also discussed in the previous lecture. This data suggests that the nuclear forces are having only spin, and again, I told you in that lecture that usually question is asked from the deuteron. So again, the question is of a deuteron, and the properties of the nuclear forces are given. Only spin and isospin dependence nuclear forces, right? Uh, so it is not true, right? No spin dependence, right? And no tensor. It is also wrong, not true, because nuclear forces are spin dependence and they have tensor components, right? Although this tensor word is new for all the UG students, although in PG it is discussed there in different courses, but we have to remember that the nuclear forces contain tensor component, and spin dependence is discussed already when I discussed the property of nuclear forces, that they are spin dependent, and this is the thing that we have to remember, that they have tensor components, right? So, but these two options are straight away dropped. No spin dependence, only spin and isospin, because they are not talking about the tensor, right? These are dropped, right? And this is also no tensor, dropped. So this is the correct answer, right? Now the next question is, which of the following set corresponds to fundamental particles? Now here I have taken this question, although this question is related to the elementary particle, but here the option that is given, right, it is wrong. Following set corresponds to fundamental particle. Fundamental particles means 6 leptons and 6 quarks, right? These are the fundamental particle, plus you can has field particles also, right? Photon, gluon, graviton, W and Z bosons. These are fundamental particles, right? So here the they have given the answer A, but proton is not a fundamental particle, neutron is not a fundamental particle, again proton is there, right? And electron, photon and neutrino, right? Quark, electron and meson. Meson is again not a fundamental particle. So the correct option is electron, photon and neutrino. These are the fundamental particles, right? Because they do not have a substructure, right? But here meson have the substructure, right? Proton has the substructure, neutron have the, so these options are dropped, this one and this one. So the correct answer is C is the correct answer, right? Next question is, which of the following is a fermion? Fermion means having half integral spin, 1 by 2 h cut, 3 by 2 h cut, so on, right? So if we look at the alpha particle, it is a boson. We know very well. Deuteron is also a boson having spin 1, right? What about this 4 beryllium 7? Now it is a even odd nucleus. We can see here, and I have discussed that even odd even nucleus have a half integral spin, 1 by 2, 3 by 2, 5 by 2. So it is a fermion, right? It is clear. As far as hydrogen atom is concerned, now if we want to take the guess of hydrogen atom, they're talking about the atom. So we have to look at the number of particles that are contained in hydrogen atom, right? So if I look at hydrogen atom, right, hydrogen atom have, if it has, one proton, right, you can see, plus electron, right? So proton has 3 quarks, right, up, down, and right, 1 electron. So it is a combination of 4 fermions. So 4 fermions when joined, right, it can lead to the integral spin, right? So we can't say that this is a fermion, right? So the exact fermion, or the given option that is 100% fermion, it is this one. So this is the correct answer, right? And these others are not fermions, right? Going to the next question. Which of the following statement is not correct? A deuteron can be disintegrated by irradiating it with gamma ray of energy 4 mega electron volt, right? A deuteron has no excited state. It is true, right? It is true. We know very well. A deuteron has no electric quadrupole. It is wrong, right? So I told you, if you don't know all the properties of deuteron, you can even make a guess, because you know its spin, isospin, quadrupole moment, magnetic dipole moment. So the answer is this one. Deuteron has no electric quadrupole moment. This is wrong. Forget about the other options. So this is the correct answer, right? Now, electromagnetic interactions are, we know very well that EM interactions conserve parity, conserve charge conjugation, conserve time reversal. All these symmetry operations are invariant for electromagnetic interaction, or they are conserved. So they are asking interactions are, this is true, charge conserving, yes. C not conserving, wrong, right? CP not conserving, but CPT conserving, right? It is again wrong. CPT not conserving, it is absolutely wrong, because according to CPT theorem, all the interactions are invariant, right? So the correct answer is A. You can see here. So this question is actually from the particle physics, but I have taken it here because it is linked with the symmetry operations. I saw this question, so I also take up this question, right? You can see the number of questions asked from the high energy physics or particle physics here in this paper also, right, in GATE exam. Now, a massive particle X in free space decays spontaneously into 2 photons, right? X gives you gamma ray photon, or we can say simple 2 photons, right? Which of the statement is true for X? X is charged. So look at the charge conservation, right? 0, 0. So if it is charged, either it is positively charged or negatively charged, the charge conservation will be violated. So this is wrong. Spin of X must be greater than or equal to 2. Let's look at the spin, right? Spin of this particle is 1, this particle is 1. So 1 plus 1 can be 2, 1 minus 1 can be 0. Two options are there, right? So this option is doubtful. I mean, it can be true, but look at the other options also. X is a boson. X is a boson, right? So if you look at the boson right here, then this is also a boson, right? And this is also a boson, right? So it means, right, this option is obviously true, because these two particles are boson. So this should be a boson also, right? X must be a baryon, right? X must be a baryon. But if this is baryon, X is baryon, then it will obviously have baryon number either plus or +1 or -1. But these two are not baryons. For them it is 0, 0. So baryon number won't be conserved. So this option is dropped, right? So the option, this one and this one, spin of X must be greater than or equal to 2. But it is again wrong. It can be 0, right? So it means this option is also wrong. But the correct answer that can be there, X is a boson. So C is the correct answer. You can see from here, the spin of X can be either 0, 1 or 2, but 1 is not allowed. It can be 0 or 2, right? Therefore, this option is also wrong. So C is the correct answer, right? So these were the questions that I discussed from the previous year GATE papers. So in this lecture, I have covered the questions from the JAM exam and GATE exam, right? I covered all the questions that were linked with the basic properties of atomic nucleus, right? So thank you very much.